thank you very much. Okay, my name is Antonio Lázaro. I'm a professor at Carlos III University in Madrid, in Spain. And also I am the CTO of a spin-off company of the Carlos III University. The name of the company is SmartCtrl. And we are focused on develop some products in the field of the control for power electronics. Okay, we are the developers of SmartCtrl. That is the purpose of the presentation of today. But also we are developing in the company control boards, rapid control prototyping system, hardware in the loop, customized hardware in the loop systems, and IP cores for controllers, test bench, and many other products in the field about the power electronics control. Today we are going to focus on the three-phase boost rectifier. It's a very well-known topology to implement an AC/DC converter with power factor correction, PFC, and this is a two-level converter, so this is a very simple topology. It's a very high efficient solution, so you can increase the power density, and it's a very cost-effective solution. Of course, we know very well about the three levels topologies that has some advantages, but still we have a lot of these converters in many key applications like power supplies for data centers, EV chargers, the motor drive front ends, even onboard rectifiers, and of course UPS. So this is why we are going to select this topology. Which are the main challenge in order to design this converter and also the control loops for this converter? One of them, from the point of view of the power state, is the EMI filter. We need to design and optimize the EMI filter. The second one is to make a proper selection about the main filter. Basically, we have a couple of options: a simple L filter like this, or you can also think about the LCL filter. So you need to select one of the two possibilities, and of course to design the electrical values and the physical design of the inductors, capacitors, etc. From the control point of view, you need to take into account the PWM modulator. There's not a single possibility. There's a lot of different possibilities: space vector modulation, discontinuous modulation, optimized modulation, etc. So you can select different options here. And then you need to design the current control, the DC voltage control, and in the case of a DQ control, that this is something that we are going to review later, you need to have some algorithm to synchronize with the grid voltage. I am talking about the PLL. Okay. Additionally, when you want to have a good design for the current control and of course for the voltage control, something that you need to take into account is that you need a good model. You need to include in your design of the control loops, of the constants, of the PI controllers or PID controllers. First, you need to have a good model, not only for the power states, but also for the analog and digital change of the measurements. I mean, you need to measure correctly the AC voltage, the AC current, and the output DC voltage. And when I say accurate model, I am talking about to take into account all the elements that belongs to this measurement chain that are composed of basically two parts: the analog part and later the digital one. So this is something that we need to take into account. Of course, you need, because we have an input EMI filter, something that you need to test when you are designing the current control and the DC voltage control is the possible instability that will be produced by the mismatch between the impedance, the output impedance of the EMI filter and the input impedance of the power converter. When I say here power converter, I am talking about the complete power filter together with the control loops of the converter. Okay, So in order to comply with all these challenges, what SmartCtrl provides are some special functionalities. One of them is a visual capability and interactive capability to design the control loops. We are going to see later that this is more or less easy to select the design point. Additionally, we are going to be able, by means of this tool, to generate automatically C code of all the control algorithms, and of course, we are able to make an automatic schematic generation for the SIMBA simulator. So the last option is to generate the complete schematic of the total circuit that you have, including the EMI filter, the main power filter, the power state, and all the control loops at the same time. Okay, in order to test in the SIMBA simulator if your control design has been correct or not, or even if the EMI filter works properly or not. Okay, let's review in some detail each of these challenges that I have mentioned here. First one is the EMI filter. SmartCtrl will support different structure for the EMI filter, up to 4 different structures. So in this first version of this functionality, for the moment, we have the capability to provide the different elements of the EMI filter. We have in the roadmap the capability to design. Okay, we are going to the next step in the SmartCtrl development is to design the EMI filter, including the quasi-peak calculation and parasitic elements for the filter. Okay, but for the moment, at least we are able to plot for some given values of these elements, the common mode and the differential mode inductors and capacitors. At least we are able to plot the attenuation of the filter in both modes, okay, in order to test if the attenuation is enough or not. Okay, right. So you can check the attenuation with this plot, and then we are going to have the complete model internally in SmartCtrl. We have the complete model of this filter in order to calculate the interaction, for example, with the control loops of the converter. The second one is the selection of the main power filter. As I have mentioned, you have basically 2 options: the simple L filter and also the LCL filter. In this second case, we have different possibilities in order to take into account the damping of the filter. You can consider just a simple passive damping by means of some resistor in series with the capacitor, or also some active damping for this filter, including an additional current control loop measuring the capacitor current. Okay, so you can select here whatever in the main filter option. In this drop-down menu, you can select these different options: L, LCL, LCL plus passive damping, LCL plus active damping, right? Regarding the power stage, it's a very simple window in which we are going to include the values for the RMS value for the grid voltage, the line frequency. This is very useful in the case of the aircraft generator. You can change here from 15 to 400 Hz, and you can now design in order to take into account this frequency range. Okay, and you can provide values for the rest of the parameters of the power stage, the filters valued, and also we can add some parasitics. We can consider some parasitics within all the inductor, the filter capacitor, etc. Regarding the control types, you can select basically 2 families of current controls. Okay, the alpha beta control, okay, the stationary frame control, or the DQ control, like this. Okay, so basically you need to select which type of controller are you going to implement. In the case of if you are selected before the DQ control, you need to select which is the type of PLL that you are going to use, a simple synchronous reference frame PLL or a more complicated one, more sophisticated one, the quadrature signal generator plus again the SRF PLL. In this case, if you consider that you are going to have some imbalance in the grid voltage, probably you need to use this second type of PLL. Okay, but anyway, at least you can select and design these two types of synchronization elements. Okay, regarding, as I have mentioned before, you need to take into account all the details about the sensing chain. Why? Because the measurement of the magnitudes are very, very closely related with the final performance of the control loop. If you have not a good model for this measurement change, probably your control loop is not going to work properly. Or if you have a very simplified model for this measurement change, probably your PI constant has not been correctly calculated. So in the case of SmartCtrl, we are going to have a complete section to provide some parameters about the current transducer, some signal conditioning. Probably you can add an anti-aliasing filter, second order probably, or first order filter. Then you need to provide the different parameters for the ADC, the type of digital filter that you are going to use, and something that this is also interesting is to obtain the constant if you want to operate with the unity gain feedback. It's the inverse gain of all the blocks around the measurement chain. Okay, so you have in SmartCtrl, you have the possibility to select the different blocks. You can simplify this structure. If you don't want some signal conditioning, you can skip this part, okay? But if you want to include it, you have the possibility to provide some information about this element here, the bandwidth, basically, the gain, etc. In addition, you can also select which is the type of modulating technique that you are going to use. When I say modulating technique, I'm not talking about the PWM strategy. I'm just talking about if you are going to update the modulating signal, you are going to compare the modulating signal just once per switching period, a couple of times per switching period, 4 times, etc. So you can select here single update, double update, multiple update, etc. And in order to consider the sampling technique, I am talking about which is the strategy to take the samples. Okay, you can, for example, use a synchronized sampling. You are going to take the samples of the current and voltages in the peak and valley values of the carrier waveform of the modulator, or you can, for example, use an oversampling technique and later use a digital filter. So all the possibilities can be taken into account. The only thing that you need to do is to select which is your preferred option, right? Okay. Now, this is more or less, this is the main window in order to design the control loops. Once you have provided the program with all the data, with all the parameters about the power states, the EMI filter, the main power filter, the sensing change for currents, voltages, etc., the PLL, all these parameters, now you are able to design the loop. Okay, we have a complete internal dynamic model for all the power states and all these blocks, and the only thing that you need to do is to select numerically the phase margin on crossover frequency that you want, you can do that graphically by means of a specific type of control that we name as solutions map. The solutions map basically is like the safe operating area for the stable solutions when you have in the vertical axis the phase margin and in the horizontal axis the crossover frequency, okay? Or even you can select, for example, to make a sweep about phase margin or crossover frequency, or if you prefer, KP and TI. KP and TI are the parameters of the PI controller for the current loop, okay? When you move this design point of these sliders here, what you are going to obtain is the open loop gain, and you can perform the open loop gain analysis, stability analysis, in order to check if finally for this constant, the current loop will be stable or not. The same thing for the outer voltage loop. Okay. In this case, in this specific topology, in this specific converter, something that can happen sometimes is the dynamic interaction between the output impedance of the EMI filter and the input impedance of the three-phase rectifier. Okay, so in SmartCtrl you can perform at the same time that you are seeing the loop gains, and you check the stability analysis in terms of the open loop gain. Okay, at the same time you can check, for example, here, which is the matching between the output impedance of the filter and the input impedance of the filter. We have here a couple of stability criterions in terms of these two stabilities, and SmartCtrl has the capability to measure the phase difference for the crossing point when the two impedances are equal, which is the phase difference between them. In terms of this phase difference, we can establish a new stability criterion, and the program is going to provide you this information. Okay, for example, in that case, we have selected here a phase margin of 50 degrees for the inner current loop, a crossover frequency of 7 kilohertz. For the outer loop, we have 50 degrees for the phase margin and just a crossover frequency of 150 hertz. So in that case, everything is stable. The two stability tests are positive. So in that case, you have, this is a stable solution. However, if you increase, everything is equal. However, if you just increase just a little bit the bandwidth of the outer loop, in that case, the phase difference is too big. You need to take into account that if you modify the outer voltage loop, the inner loop is going to be still stable. However, if you check the impedance test, you will realize that the phase difference in that case is going to be very big, and the program is going to provide you the information about that the system, the prediction that the program is done here is that the system will not be stable. Okay.
I'm sorry to interrupt. Antonio, you have basically 1 or 2 minutes left. Sorry about that.
Okay. Right. So which are the outputs of the program? Basically, you have a complete schematic vision. You have some input data panel and output data panel. And at the same time, you have the possibility, if you modify the design point, all the numerical values will update it at the same time. So finally, we have the possibility to export the complete C code of all this control structure, including the modulator, the control loops, the PLL, the ADC management circuit, etc. Okay, and of course you can export to SIMBA. I am going to try to do just a very simple demonstration in 1 minute. Okay, so I'm going to skip this and I'm going to open SmartCtrl. Today we have a lot of different internal models for many different topologies.
We cannot see your screen,
okay,
Antonio.
Okay. Sorry for that.
No worries.
Can you see the screen now?
Yes, we can see it.
Yes. So I mentioned that we are going to design a three-phase. We have a lot of different type of converters, dual active bridge, back, boost, flyback, forward, etc. But today we are going to design a three-phase converter. Okay, we are going to start with a single line diagram. In this case, we are going to select, for example, the type of main filter. I'm going to select a structure for a structure number 2 for the EMI filter. I'm going to just change a little bit the parameters of the EMI filter. 4.7K. You can check here the attenuation of all of them. Okay, I'm going to close that. And I'm going directly, I cannot spend time providing all the parameters. I'm going to directly to show you how to design. This is the compensators. This is for the current. This one for the voltage. We have here the solutions map for the current and voltage. And finally, you have here this is the loop, the inner current loop gain open loop, the open loop gain for the inner current loop. This is the test about the impedances. This is the output impedance of the EMI filter, and this is the DQ input impedance of the converter. Okay, so if we select, for example, this example, we are going directly to move to export this. This is the schematic. This is the complete schematic that we are going to consider here. Okay, and now we are going to export to SIMBA. Yes, developing the Python script. Now SIMBA is open, and you can see here how the complete schematic that we have shown you has been created by means of the Python script.
Antonio.
Sorry, Antonio, we cannot see SIMBA. We can. I think you just shared SmartCtrl.
Oh, sorry for that.
Oh, no worries at all.
I'm going to here and here. Okay,
it's okay now.
Okay, so you can see here the schematic of the complete schematic that we have placed in SIMBA, and now we are going to run the simulation. These are the currents through the inductors. Okay, we are going to add a new chart to provide the information about the output voltage. Okay, so the design of the PFC controls in 5 minutes. Okay, that's all from my side.
It was actually faster than 5 minutes, huh? It was
right.
Probably 2 minutes.
2 minutes. So That's all from my side. You have the all the presenters. You have my email in the first slide. I'm going to ask Emmanuel to share the slides with all the audience. So you have my contact there if you need some doubts or some questions. Thank you very much.
Thanks.